So what do we have to go through? Anybody know? We have to go through something called an analog to digital converter, an ADC. And then when we output, if we're going to output to that analog port, we have to go through a digital to analog converter. So what the ADC does, we have different things. We can go to single bit A to D converters, which we see on a lot of our sensors over there, right? You understand? Where the sensing element itself is an analog sensor, but yet inside the electronics that run the sensor converts that analog over to a digital. So what we do is most of them give us the ability to set what we call a threshold. So we can set when the sensor switches from a 1 to a 0 or vice versa. Then we have true analog signals. And what we do is we bring it into and we do this different method, which we're not going to talk about here. One method is what they call integration, which is basically that's what your meter uses. And basically the way it works is they set the A to D converter to a reference voltage, and then they generate a linear slope. It's not a slope, it's a linear line. And then they switch it over to the to the input unknown, and then they start a counter counting. And then they count it until it crosses 0, and when it crosses 0, that means that's the actual count. So this is why meters, when you get into meters, they're rated in counts. We have 2,000 count meters, we have 4,000 count meters, and we have 6,000 count meters. And you can see where it ranges. So a 2,000 count meter would range on 1999, right? So as soon as it got to 199, 1999, then it would automatically do what? Range. And this is one major reason why your meter does not use legal scientific notation. So as soon as it got up to 199.9 ohms, it would range up to K. And then it might show 0.135 K, and everybody wants to say 0.235 K. They want to put that down when it's actually 253 ohms, right? You understand? So our PLC A to D converter, that's exactly what it does. So what we do to figure out what's going on, we come up here and we need to know the number of counts that's available from the A to D converter. This A to D converter is what we call a 10-bit converter. So what we would do is figure out how many counts we would get, and I would come up here and I'd raise 2 up to that power, and that means we'd get 1,024 counts. But one of the counts is 0, so that would be 1,023 counts. Now, standard input for PLCs for analog is 0 to 10 volts, or 0 to 5 volts. This PLC compensates for it. Allen-Bradley doesn't compensate for it. So if we use use 5 volts, then we'd only get 511 counts, right? Does that make sense? We only get half the available counts. So what we would do is to figure out what binary number rated something, we called it a transfer function, and I would take 10, which is the maximum voltage we get it out, and then I would come up here and I would divide it by the number of counts, and it means we would get one count for roughly every 10 millivolts. So if I had 10 millivolts, it would count to 1. If I had 20 millivolts, it would what? Count to 2. If I had 3 millivolts, I would get a binary count of 3, and it would go up. So this would be the kind of math I would have to do to make the counts mean something, right? You understand? Technically, we refer to this as a transfer function. So what I would have to do in the Allen-Bradley PLC is I would have to come up and I would have to take my input, right? You understand? And then I would have to reference that to an actual value. Does that make sense? So what I would do is I would calculate the transfer function, and when I got a number, I would come up here and I would multiply it by a transfer function and make it mean something like 32 degrees or this or that, right? Does that make sense? So what we're trying to do is we're trying to get a count over to a unit that we're dealing with. Well, A to D converters have been around so long that, of course, the more and more they move up the field inside PLCs, the more likelihood they're going to add instructions that allow us to do what? Do the math for us, right? You understand? So Siemens has an instruction called normalize, which basically means we can take something and we can convert it over to something else, right? That makes sense. So I can take the count and then I can convert it over to the fraction that represents. Does that make sense? Okay, the fraction of 10. So we'll start off. So what we see is we see a count, but yet that count comes up and actually equals to around 10 millivolts per count, right? You understand? So I just did it mathematically, but inside the PLC, it seems like they should have a what? An instruction to actually do that. So Siemens supports an instruction called normalize that allows us to take it in one unit and do what? Convert it over to another, which is really, really slick, guys. And I might have to go back and look up this. I thought I had a program already written. Now we can find it over here, but this little box right here that's got the question marks in it. What is that? That's all the instructions available to us in the PLC. So I can just come up here and start typing in normalize X, and then I'm through, and I don't have to. Once I understand my instructions, right? You understand? Then it's a lot faster to use that than just try to go over in our scroll bar and do that. So this is where we come up and we normalize something to something, right? Over on this side, we decide what type of numbers are we bringing in. So I'm going to come in from an A to D converter, and when we talk about A to D conversion, it's 1,023 counts, and that's no fractions or anything on the left coming in on the left-hand side, right? You understand? So what type of number would that be? We got to go up to 16 bits, so we're going to use a double integer, right? You understand? So I'm inputting a double integer. But when I come up here and divide that by 1,023, then that's going to be a what type of number? It's going to be a real number, right? You understand? So I'll say I'm going to come over here and I'm going to output a what? Over here I'm going to output a real number, right? That makes sense? What did the other option say? This is what we went over there, all these different numbers we have available. So we have an integer. Now if I use int, that is an 8-bit number, that's a byte. If I use dint, then that's a double integer, that's 16 bits, right? Then we have signed integers and we have unsigned integers. So if I use an integer, then it has the ability to be what? Positive or negative. Well, literally on my we can come up here and change that. So literally over here, I think this is 16 bits. We need to make sure it's got to be 16 bits. I could come up here and use that because my count, what I'm getting off my AD converter is always positive, right? You understand that? It doesn't never go negative. That makes sense? USINT. Okay. Now I'm new to this too, but we've got on your website, hopefully. I'm gonna come over and bring this up and just to make sure. So we have what we call what they refer to as data types. So. Real or what was that second option? Yeah, a long real number. That's the 64-bit number, right? Yeah, I know it's small. I'm sorry. So here we got what they call data types. Oh, data types. And like I said, I'm used to this too. No, this is not what I wanted. This just shows the range of the data types. I did that one. Oh, here we go. No, that's not it either, guys. Okay. Oh, this is it. So I had it right the first time. So Boolean, these are single bit. Bytes are what? 8 bits, words are 16 bits. Then we have these SINT, these are signed integers, unsigned integers, and double integers. This is I still have all of them. Where did I see that, guys? I got it somewhere. I'm missing out of this. I need to go back and actually look at this because I had to pull this together myself. That other one I actually got off of on somebody's site.
You said that was wrong, right? When you pull somebody's site.
No, it's not. It wasn't wrong. We figured out. We figured out it was right. What I was looking at was the actual values, but it's not the values, it's the number of addresses that are available. So when we was looking at it, I was saying this was wrong because I was trying to see how many combinations that were available in that number system. But what they're giving me is the number of address ranges that are available. And that's why we got to 0.7 because these are Boolean. So I can go from 0.0 up to 65,535.7. So that's the legal addressing range for input, right? But you got to have an input out there. You just can't make up input. You can't make up output. It all depends on the size of your PLC. But this is the addressing range they support. Now you remember on RSLogic 500 it was 0 to 256, right? You understand that? Here, this is what? This should meet almost any application that we have. So when they're doing this is just the addressing range available. How many byte addresses do we have? Well, if we have from 0 to 65,535, what you have to remember is that for every byte address you use, it's going to eat up a whole byte of memory, right? You understand? If you use that byte of memory, then odds are you might not be able to use it as a bit, even though you still can. They're saying, okay, I can come in and I can set a whole word, or I can set a single bit inside the word. So that's what we're doing when we clear out all our outputs. When we do our reset or when we do our e-stop, we're just going out there and clearing out Q, right? So we're addressing a whole word, but then in our program we come back and we address individual bits to actually control. But it's up to you to remember what's going on, right? Y'all understand? So makes it a little more complicated. So this is where we was talking about it being. I was saying they were wrong, but they're not wrong because they're not showing me. They're not showing me the value. They're showing me the number of addresses that's available within those values, which is pretty neat. But most of us understand, and we teach that pretty good in PLCs. Bytes, words, double words, right? You understand that? And of course what Alan Bradley did, and like I said, I need to learn the 5000. But what RSLogic 500 did, it dedicates memory to certain types of data, right? like F8 and N7 and stuff like that. What Siemens, or what this application does is it allows you to control your memory. But now you got to keep up with, I've already used this, or I already used that, and that kind of stuff, right? Because if you use QW, it's not going to say, well, you're already using QW, you're already using that word for something else. It's not going to tell you that, right? Unless you assign a tag to that word. But you don't have a tag assigned to the bit. Does that make sense? So you won't, if you try to reuse the same word and you've already assigned a tag to it, then it'll pop up and give you that tag. If you assign a bit inside that word, it's not going to give you an error because that bit has not been assigned, right? Does that make sense? So what we'll do is, like I said, guys, I might have to go back and research this a little more. So what we're going to do, of course, is we're going to come up here and we're going to assign it a minimum value. So you can actually set the reference to a minimum value, right? You understand? So of course our minimum value is going to be 0, and then our maximum value is going to be what? 1023. That's not too bad, is it? And then of course, where are we going to get our value from? The address assigned to that port. All right. So that's not the hardware identifier. That's the actual address. So we're still offline. So let's go back and look at that real fast. I'm gonna go back to properties, right? And then I'm down to IO, right? And I'm looking at my analog inputs, and I'm looking at my hardware addresses. So what I would do is I would address it as 64. That's the one. So I can reassign this, and the other, it automatically takes 3 bytes of memory. So if I come up and reassign this, so I can assign this address, it's a logical address, but then it'll automatically add 3 to that and put it where I want to, right? Of course, 64 is okay. Are we okay?
So you said you assigned it to 64 and it automatically?
No, it automatically assigned it 64. So it automatically stuck at an address that's outside of what we use. It's just like when we come up here and set up our memory, it automatically assigned it memory byte 0 and 1. And of course, what we wanted to do is we wanted to use what? 0 and 1. So to make it easier to translate the Allen Bradley addresses over to the Siemens addresses. So we got, we got B3 0/0, and we can make it M, right? M0/0, .0. It just made it a lot easier to do that. So all these guys are assigned ports. We're looking at analog input 2. And that's what I can't figure out because we got two analog ports built into the PLC. They're over on the I didn't hook my camera up. They're over on the right hand side. And the 1100s that y'all deal with over in the lab, those are really basic PLCs. The 1100s that we have, that hopefully eventually we can start using, 1100s that we have 2 analog inputs on. What we've done with our PLC is not only does it have the 2 analog inputs, which are over here on the left as soon as my camera comes up. I don't know. It says I'm blocked from that site, which is an adult site, guys. It's an adult site. I don't know what it's trying to do. Believe me, right here, see category. Okay, fine. Now the analog inputs are right here. Then it's got AN0 and AN1 and then 2M. So what's it looking for right here? It's looking for a common, right? Understand? So it's a sinking input. But what we can do over here, instead of putting digital values on it, we can come in here and put analog values on it. So any analog sensor that's out there. Now what I have wired up, I don't know if you can see, is I'm simulating it with a potentiometer. So what I can do when I turn my pod, and it's the way you would wire your sensor up is so you would have to have a dedicated power supply, and it's got to be a really good power supply, because if you put a bad power supply on there and it's fluctuating, then your analog input's going to do what? It's going to fluctuate. So standard input on, now you can use a 24 volt supply, but what you've done is you've limited the range. And a lot of your analog sensors will power up on 24 volts, but they only give you from 0 to 10 volts when they output, right? Does that make sense? It's like our device over there. Or you can come in and use other methods to get the 10 volts. I've got mine hooked right across a 24 volt supply. So as soon as I exceed 10 volts, a big red light comes up and starts flashing on my PLC saying that I exceeded the range, right? So we'll come up there and we'll do that on purpose. So the way I have the circuit wired up, and it's a pretty simple circuit. So I've got mine wired up to 24 volts because I don't have another power supply over here. Because I'm running mine on a potentiometer. So what do we use potentiometers for? What does potentiometers do for us? What do we use? What's the main? So we got rheostats. We got rheostats, right? And then we got potentiometers.
That's when you call a pot, ain't it?
Yeah, that's pot for short. Yeah. Yeah. So y'all hear what Justin said is for us to control the voltage. So back in DC, you learned about voltage dividers, and this is where we use resistors to set a voltage that we want. So I could literally come in and hook up a voltage divider and get 10 volts into my pot, right? That makes sense. Of course, it would take a little more math. What we're doing with the pod is we have the ability, if we set the pot all the way up to the top, then what we'll get is we'll get our supply voltage. Our supply voltage will come out our wiper. If I set it all the way down to the bottom, then we should get 0 volts, right? That makes sense. And if I set it somewhere in the middle, then we're going to get a ratio of the voltage. Then we come up with this guy right here, which is basically a voltage divider. But I have the ability to adjust the top resistor and the bottom resistor by where I put my wiper at. So what I'm doing is I'm putting plus 24 volts here, and then down here, 24. Yeah, I said 24, but 12 up there. Thank you. My brain works in mysterious ways. So I'm putting plus 24 volts right here, and then down here, this is 0 volts. So I should be able to get any voltage between what? 0 and 24. Any voltage I want to. It's just as accurate as finely as you can turn that knob. You could get literally any voltage you want to. That makes sense. Well, technically, a potentiometer is a variable voltage divider. That's what it is. It's a variable voltage divider. So what I'm doing is I'm setting these two resistors right here. So if it's a 10K pot, if this was 3K, then down here, this would have to be 7K. Because that's, when they say it's a 10K pot, that's the maximum, that's the resistance that you're dividing up. And then I could come up here and I could calculate this, right? You understand? And this guy right here would drop 7/10 of the voltage. This guy right here would drop 3/10 of the voltage. It's a 10K pot. But I could literally set anything I wanted to, right? You understand? If we use what we call a linear taper pot. And of course, I could calculate the voltage that I would get out of here. Now, the problem over here is when I bring this into the analog input of my PLC, and I'm using 0, what it's going to look for is from 0 to 10 volts. So it's got two ranges you can set up. You can set up 0 to 10 volts or 0 to 5 volts. Allen Bradley don't give you the ability to set the range. It's either 0 to 10 volts or nothing. That makes sense? Y'all follow me so far? So that means on an Allen Bradley, on the 1100 PLCs, if I only bring in a 5-volt analog input, then I'm losing half my counts. Instead of getting 1024, I'm only getting 511, right? Does that make sense? Okay. So I wouldn't have as good a resolution if on 5 volts that I do on 10 volts. So if I exceed 10 volts on this input, then what it'll do is the PLC will give me an error. It won't hurt anything, it'll just give me an error. Which means your input has exceeded the range that's allowed on the analog input. Does that make sense? And we'll force that error. Yeah, when I first hooked it up, I had the pot set too high, and it turned on and red light started flashing, and I was saying, "What did you do, Rich?" And then I realized that I'd what? Set it too high. As soon as you drop down within the range, the fault will come out. It'll come out of the fault by itself. So what I've done is my pot. So I had to connect my pot like this, right? You understand? Across here. So I've got one lead of my pot going to one of my M's. I got one end of my pot going to my L's. And then this comes into the PLC analog input. And then it's got to have its own what? It's got to have its own M, right? That makes sense? So I'd have to do this on my analog sensor, but normally on your analog sensor, it's going to be referenced to common anyway, right? You understand? And then would power the sensor up, and then the sensor would give me the range. And normal range for an analog sensor is 0 to 10 volts. That's what I'm using here. It's not. We're using the power. I'm using the power supply inside the PLC, but you don't have to do that. I could come over here and put a plus 10 volt supply that's somewhere else. But what you'll have to do is that on that power supply. So let's say I had an external power supply. Well, what I've got to do is I've got to reference this to that. That's all you got to do. Just reference it to the same common. That's what a common is. And we can have multiple power supplies hooked up to the same common, right? You understand? And then I could take my 10 volts and I could come up here and then it would apply to my sensor. All I got to do is take this and hook it up to one of my M's that's hooked up to my common M that runs through the whole system, right? Does that make sense? Yeah, I could use 5-volt supplies. I could use just about anything I want. All I got to do is just make sure that I do what? That I establish the common for the system. So that's a good question. Any more? So yeah, I could bring another power supply. I could set it up here. I could set it to 10 volts. I could hook my pot. I could take the top of my pot instead of hooking it to my L. I could hook it to the positive on the power supply, and then I could set it for 10 volts, and I wouldn't have any error, right? Now, normally on these sensors, these analog sensors that we have available to us, they will power up off of 24 volts, and then this would be an M. But when they output from 0 to 10 volts. So they have the voltage converter inside the sensor. Does that make sense? And so 0 to 10 volts is pretty common for analog in the processing world. It's just like 24 is a standard power supply that we use for our PLCs. And even though we do have some PLCs that have their own AC to DC converter built into them, right? You understand that. In fact, this PLC here. So this is a Siemens 1200 PLC. I'm not important, but this is an AC DC relay. So you notice on this guy, I have a power cord in this. This guy here plugs in 120 volts DC. Then it's got a built-in power supply, which is a 24 volt power supply that I can use out there on my input devices, because all the inputs are DC inputs. So on PLCs, if it says DC, it's talking about plus 24 volts on PLCs. That's just the standard that we use now. So that's an AC. This is a DC, 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 which means what? I have to power it on a 24 volts, right? You understand? The inputs are DC, so it means they're going to be DC inputs, and then it's going to be DC outputs, right? You understand? That guy is what we call an AC DC relay. So that means I've got to put 120 volts on that thing, and it's right. And then you have to figure out, is it 124 volts or 240? So we have a lot of AC PLCs out there that run on 240. So there's a lot of industry that don't have 120 volts available out there in the control. And why? Because 120 volts is fairly. What advantage does high voltage have over low voltage? Less current to produce the power, right? You understand? Which means I can use what? I can use smaller gauge wire inside my system, which means it's going to be a lot cheaper to install. It's not more efficient. It's just cheaper to install and cheaper to run, right? So there are PLCs out there that's rated on 240 volts AC. But then on their DC outputs, their inputs are probably going to be DC inputs, right? You understand? So they'll have a power supply built into them. So our PLC has a power supply built into it. The Siemens over there, the RS Logix over there doesn't have a power supply built into it, so we have to run an external power supply. The 314s do not have an internal power supply, so what does that mean? We have to have an external power supply. So if you look at the Amatrol line, you'll see every one of them's got a what? Got a power supply. And then when y'all go back and convert put your Siemens PLC in the back, you're going to have to disconnect the power supply in the back, because ours is powered up through the power supply that's on the thing. So that makes sense? Everybody okay? So what we would do is we would come up here and we would normalize this. I call it normalize. And then and this is what I might have to go back and look at, because we have two channels, and yet I'm only given one address. So this is analog in2, but I don't see analog in. There's two analog inputs. Oh, here we go. So here's channel 0. This is the one I need to look at. And this is channel 1. And it looks like, I'll have to figure this out. It looks like they both have the same address on it. By the way, when I clicked on it, it gave me the addresses that were right. Y'all see that? So what I would do over here on this one, I would put my value would be coming from what was it? Input. Yeah, but it's probably going to be a word. We need to look at that. And then I would put the 64, and we'll see if it comes up and gives us an error. Input word 64. Okay. I don't know why I got an error first. Yeah, I put IW64. So I'm gonna have to go back and research this. So it's when I put 123 down here on the max value, it is what? And what does that mean? That means I'm doing something wrong. And the problem is I already had the program written. I just can't find it. So enable input, enable output, minimum value, low limit of the value range, normalized value. So value is the value to be normalized. We can get it from an input. Max, this is the high limit of the value range. And then my output is the result of the value. So it looks like I'm doing it right, don't it? So what I need to do is check and see exactly what the range of the thing is. You know, let's see if it gives us that. Was that? It is going to be unsigned up. But we could come up here and use an integer. You'd like that. It could be an integer because we're only going up to 1,023, and our integer gives us up to 57. And then my output, we're going to have to assign this. This is going to be a real number over here. And I'm going to have to assign it to a so this is a real number. That's what I got to figure out. So I'm assigning it in a word. There we go. That's a double word. That'd be 16 bits because it's. So then we can assign tags. I'm just going to leave them like they are. But what should happen now when I put my input in on this one, it should come up and give me a fraction. That's basically the transfer function, right? So it should come up and give me from 0 to 100%. See that? So we'll download it in VLC. And then I'll do a little math to actually convert it over to what we're trying to get it to. So it's got another program in there. So what do I need to do? I need to continue without synchronizing, right? Then we need to do what? Then we need to stop all. Then we need to load. Then we need to finish. Then we'll go online and so over here, so what over here is set up. What basically is done. How would I change it over if I wanted to? What I'm going to do is I'm going to come down here on the tag. I'm going to right click on the tag. I'm going to come up here to display format. And I'm going to go to the tag and I'm going to say do it in what? Yes. So what this is automatically doing for me is taking this value, which is coming in from my what? From my pod, and it's converting it over to this value coming over from the transfer function. So if I was to take 10 volts and divide it by 1,023 and then multiply it by this number, this is what it would do. And it's doing that for me what? Automatically. Right? That makes sense? So this normalized instruction is really, really cool. So I could do all the math. So on the Allen Bradley PLC, what I would have to do is I would come up here and I would say 10 divided by 1,023. And then that would give me that number. Then I'd say time 6689, which is what I'm getting off. That's the count I'm getting off of my. And then I would come back. I missed a number somewhere. I'm off of that. 65386, 5386. You'll see what it does for you. And it's doing all that automatically. So it's taking this, which is just an oddball value, and it's doing the transfer function for me. Then I could take this and convert this into degrees or whatever I need to do. So if 10 volts equals to 400 degrees, then I could take that and convert it over so it would display degrees too. Are we okay? So that's analog, guys. It's really, really neat. And like I said, we have analog inputs on the 1100, but it doesn't have this normalized instruction. So I'd have to do a math instruction, right? A floating point math instruction to do this conversion for us. So I wanted to show y'all that. Any questions? So D to A, what is A to D? I'm sorry, what's that? Analog digital. We have two ways we can do analog. We can do digital or 1-bit analog, which means it's gonna have a threshold. Once it exceeds the threshold, it's gonna be either what? True or false. And then we have true analog, which gives us the ability to take a analog input and generate a binary number that represents that. And what you need to know is the resolution of your how many bits it uses, right? You understand? And then what would you do? Anybody remember? Use your calculator, and then you'd raise 2 to the number of bits. Yeah. And that will come up and give me the number of counts available to us. Huh? Yeah, take away 1 because that's the number of combinations, and 0 is one of the combinations. Well, 0 doesn't actually generate a voltage level, right? And then we would divide that into the voltage that we're using, and then that would give us our what we call our transfer function. When y'all take the sensors class, if you take the sensors class, which I think is required in the AET degree, I think it's an option in the IoT degree, we'll use the transfer function, trying to figure out what the output is relative to what comes in on the input.
The sensor class is an elective in the IoT?
I think so.
I thought it was one of the 4 class.
Not in IoT, I don't think. It might be. I've a hard time keeping up with those too. I know it's in there. I know it's in both degrees. I know sensors is in both degrees. The only problem we have in the AUT is motor controls is an elective. And sensors requires motor controls. Because what we do on the sensors class is we basically hook it up in a control circuit. We don't hook it up to a PLC. We hook it up in a motor control circuit. So if you don't take motor controls, you'd come in there just totally lost.
So would it be a good idea to take motor control and sensor control at the same time?
You can't take them at the same time.
Okay.
You can take them in a different mini term. So if it's available, you can take motor controls in a T1 and then take sensors in a T2. You have to have, it's a prerequisite. So what a prerequisite is, it means you have to have this class taken before you can take this one. A co-requisite means you can do what? You can take them at the same time. Everybody okay? All right, guys. Oh, Chris. You raise your hand? Oh, okay. I didn't see. I got my glasses. All right, guys, y'all go to lab.